Okay, we're going to get started on the EV experience stage. Some great training in regards to thermal management fluid. I made a mistake. I called it coolant, but it's a thermal management fluid. And we have an actual doctor here from Prestone, Colin Dilly, and he is going to talk to you. What's the role with coolant in a battery electric vehicle? So I'll let Colin take it away.
Thank you. All right, thank you everybody for showing up. All right, today I'm here to highlight the importance of thermal management fluids in electric vehicles. I'm going to talk about the challenges involved in the development of those fluids and the concerns that will arise if unsuitable fluids are used. As we venture towards a greener and more sustainable future, electric vehicles have emerged as a game changer, promising reduced carbon emissions and improved air quality. However, to fully unleash the potential of EVs, we must not overlook the significance and value of proper thermal management and the important factors that determine the definition of a successful thermal management fluid over the vehicle's full life. At Prestone, I lead a growing team of about 28 chemists and engineers, which includes a team that's entirely focused on EV and fuel cell fluids. And I myself have almost 30 years in the industry and have witnessed very, very many changes over that time. Prestone itself has been around for almost 100 years and was the first to develop ethylene glycol-based coolants and have been at the cutting edge in the design of those fluids ever since. For example, we developed our CoreGuard technology to completely eliminate corrosion for the life of a vehicle, making it the perfect choice for the over 24 models of electric vehicles that we factory fill today. We've been working with our OE partners for at least 24 years on low conductivity fluids and for fuel cells and for other applications, and I'm going to get into those as we go through this. So, as we look at automotive electrification, it's obvious that energy management is key. From the infrastructure perspective, predictive energy management and vehicle-to-infrastructure communication can optimize energy consumption by anticipating traffic patterns, road conditions, and charging station availability. From the vehicle perspective, energy waste is reduced by intelligent power distribution systems that efficiently manage electrical flow to different vehicle components. However, the key to maximum efficiency is operating the battery at the optimum temperature. And key to optimum temperature is a thermal management fluid that is correct for the system. And I want to point out, it's certainly evident that you can't use any old technology in electric vehicles. So, a little bit of history. Even though the first ever electric vehicle predates the first internal combustion engine vehicle, there's only really been an acceleration of EV technology over the last few years. With government incentives and changes in political viewpoint, EVs are making economic sense, and each automotive manufacturer wants to ensure it gets its fair share of the market. However, only with consumer acceptance will these electric vehicle-driven positive changes occur in our environment. The fluids that 99% of electric vehicles on the road today rely on is existing old antifreeze coolant technology. Future advanced thermal management fluids will have far more efficient heat transfer, enabling weight reduction, allowing the battery to increase range, and providing environmentally friendly, sustainable, and safer options to preserve our planet. As you can see in this table, if you can see it, we have moved forward from one internal combustion engine coolant to many potential chemistries because of the unique cooling capabilities required by the new components. The largest difference being whether the components have direct exposure to the coolant or are cooled by a contained and separate cooling system. The historical version of a coolant as a commodity still makes engineers think of components first, then chemicals. We at Prestone believe that there is an argument that components can be improved and refined if the fluid used is better designed up front. If a fluid will surpass the life of a component and will not change it, or if a fluid can provide better heat transfer properties than the fluids being modeled, there are obvious advantages to be gained in the size and weight of the thermal management system. This adds the potential for more range as the batteries become more economical. Conversely, much development time is lost if that being developed leads too much of a significant challenge to the liquid or gas or solid being used to cool down that component. However, at Prestone, we do like challenges, so we're happy to take on anything. So, simple question. Why do we need to develop thermal management fluids? To put it simply, the working temperature of an electric vehicle is much higher than what is optimum for the battery. Drivers, passengers, components, all systems require different operating temperatures. Therefore, to achieve the optimum operating environment for all, a battery thermal management system is needed. And that system requires energy to operate it. Therefore, everything we can do to minimize that operating energy can be used to increase range. So range apprehension is perhaps the largest obstacle for consumers to overcome, and as unlikely as it may appear, thermal management fluids can help that range anxiety. So when a battery is too hot, life cycle, stability, power, and safety are compromised. When the battery is too cold, the power delivery and energy capabilities are significantly reduced. Therefore, simply stated, thermal management fluids allow the battery to have optimum performance, improved usage, and longer duration. So how do we test this? On the roads today, we have a number of electric vehicle fleets. However, we are very aware that the testing of the EV of tomorrow is a luxury we won't have because those vehicles don't exist yet, and the components, heat pumps, cooling systems, cooling plates are still in development. So we've moved forward to computer modeling as our mainstay for developing the futures of tomorrow. So what we're going to do, we're going to explore some of the key reasons why these fluids are indispensable in the realm of electric vehicles. But first, we're going to address some of the challenges to engineering those new fluids. So I'm going to start with what the EV needs, and then we'll look at the chemical properties required to meet those needs. So to solve the challenges of the future, we first have to understand the temperature management goals. So batteries need to be between 20 and 30 degrees C to be optimum. The motor and the power electronics need to be maintained at under 60 degrees. And each of these components requires a different set of performance properties, from lubrication to anti-corrosion to heat transfer modification. So what do we look at first? Safety. So safety is paramount in any vehicle, and EVs are definitely no exception. At Prestone, we design around safety, where there are two major categories to address. First, lifetime safety, which is affected by any type of system degradation. And secondly, event safety, which is any event that suddenly impacts the vehicle. So lifetime safety issues are Sorry about that. So lifetime safety issues are centered around ensuring the thermal management system remains uncompromised for its life. It requires no corrosion and no related leakage, and it must prevent high temperatures that can cause thermal runaway. Incident safety, such as a crash, flood, or structure fire, is much more difficult to protect against, and we need to understand exactly what chemical changes can occur in the event of a structure fire, flooding, or a crash. So one of the primary reasons for transitioning to electric vehicles is to retain reduced carbon footprint. Efficient thermal management reduces energy wasted on managing heat, so making EVs even more environmentally friendly by maximizing utilization of the energy for driving. So the theme of sustainability is vital as we develop our fluids. We believe in choosing sustainable chemical alternatives, even when those costs are higher, because using these sustainable materials now will drive a better market for those choices in the future. If we forget sustainability, carbon footprint, and environmental considerations, we're not protecting the future on this planet. Battery development is accelerating quickly. So research and development efforts are focused on improving lithium-ion batteries, exploring novel materials, and enhancing electrode design to increase energy density while reducing weight and cost. The adoption of solid-state batteries can lead to safer and more efficient EVs as they offer higher energy density, faster charging, and longer lifespan compared to traditional electrolyte batteries. However, lithium-ion or solid-state both require cooling to work efficiently. So, as we develop fluids that will regulate the temperature of these battery technologies, we take great care to ensure that the chemistry is compatible with the materials of construction. It is of a conductivity that will not cause a short circuit with electrical components and is stable enough not to deteriorate into a substance that will become harmful. Thermal management fluids must be designed around the performance needs of specific battery technology and must ensure that the battery remains within a safe and ideal temperature range during operation and through charging and discharging. So range apprehension. Range apprehension is a major hindrance to EV acceptance, and overcoming it is key to future electrification efforts. So again, by keeping the battery at the ideal temperature, thermal management fluids can help preserve battery capacity, extending the driving range and overall efficiency of the vehicle. Therefore, the better the thermal management fluid, the smaller the system and the lighter the weight. To be a better thermal management fluid, we must keep 100% of the battery cells functioning and working in an optimal temperature range with a thermal management fluid that has low energy requirements in pumping and high heat transfer properties for efficient cooling. Slow charging is another hindrance to EV acceptance, so speeding up charging is also key to electrification efforts. There is much in the works to provide enough power to electrify the vehicles of tomorrow. From renewable energy sources to vehicle-to-grid technology, which allows EVs to retain excess electricity to the grid during peak demand, improving grid stability and making EVs more economically viable for the consumer. However, no matter the infrastructure, if an EV cannot quickly use the energy provided, its acceptance will be hindered. Deployment of high-power, fast-charging stations can minimize charging time, but fast charging generates significant heat and a host of thermal challenges to overcome. So therefore, we have to make sure we address both the vehicle and the charging stations for efficient cooling. As advances are occurring in batteries and materials, a lot of lightweight materials are being used, such as carbon fiber, aluminum, polymers, high-strength steel, and all of those are used to reduce weight. Our fluids extend the advantage to protect these materials that are used in the system and contribute to the longevity and reliability of these components, ultimately reducing maintenance costs for EV efficiency. Our chemistry is designed to combat corrosion, cavitation corrosion, and provide lubrication at the right viscosity to manage thermal conditions in all components that they touch. Also, we have to work around aerodynamic enhancements. The car not has to look good, which puts a lot of pressure on what the thermal system is going to look like. Our thermal management fluids have to overcome those shortcomings and be even more efficient than they've been in the past. So, what are the key fluid properties that we have to formulate for success? So first, it does not matter what you formulate for. If that fluid does not remain unchanged for the desired life of the fluid, you're wasting your resources. With stability, it's essential to understand what happens over the life of the fluid. For example, aqueous and oil-based thermal management fluids will pick up water over the life of the vehicle, and that water changes the formulation. Conductivity and all the other properties are going to change. Other chemistries break down under heat, and the formula slowly changes its properties and no longer remains what it was at the beginning of its life. So heat transfer, boil point, freeze point, toxicity, compatibility, and especially conductivity will all change with time. For example, those of us who are working with nanomaterials, we understand that over time, if that suspension of the nanomaterials changes, that fluid is no longer what it was and often is no longer a safe fluid. So sadly, it is true that some electric vehicles today do not have fully compatible fluids in them. We believe it's critical that thermal management fluids need to be fully compatible with every component it touches or may touch. Those components, metals, plastics, gaskets, wires, polymers, and even 3D printed components need to remain unchanged by the fluid for the life of the vehicle. To think of it another way, systems, if they are negatively impacted by the fluid, need to be over-designed and are therefore overweight. And as we know, for range, every ounce counts. So on heat transfer, there are two prime heat sources in lithium-ion batteries. First, the heat discharge due to the Joule effect, and second, the heat release because of electrochemical reactions. The highest amount of heat that is generated is at the positive electrode. Therefore, primary to thermal management fluid is heat transfer capability. Required are high latent heat and high thermal conductivity, which define the heat transfer properties. Those heat transfer properties must also match the needs of the passive or active thermal management system used. Generally, the better the heat transfer, the less fluid that is needed in each system. A fluid's heat transfer may be improved by incorporating chemistries from nanoparticles to developing specific chemical ratios. So, as we develop our thermal management fluid, our eye is not just on the fluid, but on how fluids will impart value to the vehicle. Minimizing viscosity is an example of this. A lower viscous fluid is easier to pump and therefore requires less energy to pump, leaving more energy for miles to be driven. Viscosity over any given temperature range is critical to understand. In cold weather applications, when electrical availability is at its most limited, we do not want to waste energy on hard-to-pump fluids. And related to viscosity is freeze point. The fluid must be pumpable throughout the range of operating temperatures of the vehicle and not become a non-flowing solid or a hard-to-pump flush. Conversely, boil point must also be understood. There are hot spots throughout the electric vehicle, especially in the battery. And if that boiling point is overcome, we get nucleated boiling and we can get cavitation corrosion occurring in the battery or in the bearings of the electric motor. Conductivity is obviously a priority to protect the EV during an incident where fluids may come into contact with live electrical circuits and cause damage, or in immersion systems where it is designed to be in contact with live surfaces. And remember, conductivity can change with time, and engineers look at conductivity at day one. They need to look at conductivity after significant miles of driving. Durability and stability are very closely linked. The chemistries must be durable under the extreme conditions that the vehicle will be under. The various additive packages we have developed must stand up to the environment, otherwise stability is compromised. And yes, we have seen vehicles on the road where stability is compromised. So together with the electric vehicle manufacturers, we believe sustainability is the focus. We want to preserve this planet we live on and protect the environment. If we choose forever chemicals, or if we choose raw materials that cause ecological harm when made, we are really doing the industry a disservice. Our chemical choices should be sustainable, and our formulas should be recyclable. For those who have lived through the recent supply chain challenges and geopolitical issues, we understand that we have to ensure that the raw materials of our formulations are also readily and obtainable. So thermal management fluids have significant and some might say critical value-added features. But we always strive to make sure our products are economically viable to both customers and consumers. To do this, we must consider manufacturability, global availability, and cost. Some specialty chemicals can cost hundreds of dollars per gallon. We do not see that as a sustainable path forward. Therefore, we are developing suitable formulas at affordable prices, because cost-effective sustainability brings about consumer acceptance far quicker than the more expensive alternatives. So I'll address safety last in this list of fluid properties so that you walk away with this in your mind. Each of the fluid properties affects safety. Several are obvious, such as toxicity and flammability. However, to address both lifetime safety and instant safety, we must be aware of how the chemistry changes under the influence of time, or fire, or if accidentally mixed with other chemicals. For example, if a thermal management fluid is compatible with a coating, but cavitation corrosion penetrates that coating due to localized hotspots, that design-safe fluid is no longer safe. And this is happening out there. For another example, if particles of a metal or metal oxide from a corroded bearing cause nanoparticles to plate out, you no longer have a safe fluid as its properties have changed. So in a rush to put fluids in vehicles, the stability over the life of the components may not be what the engineers expected. And we have seen many examples of that in the field today. We don't want to create forever chemicals or toxic gases when an incident happens. Lifetime safety and lifetime stability are the assurance that the chemistries used do not alter the thermal management system for the lifetime of the vehicle. And what we have found as we develop new technologies is that there is a balance between all the parameters that we must consider to engineer the perfect thermal management fluid for each system. So in conclusion, as we continue to embrace electric vehicles as a viable solution for sustainable transportation, the significance of thermal management fluids cannot be overstated. They are the unsung technology heroes that work diligently behind the scenes, ensuring the seamless integration of electric vehicles into our daily lives. Thermal management fluids provide value due to their ability to help with safety, sustainability, and range. And the correct fluid choice can reduce fluid volume, reduce weight, and maintain the cooling system unchanged without the need to over-design the system. By focusing on thermal management advancements, the automotive industry can collectively work towards maximizing energy efficiency and range, which will guide stakeholders to make informed decisions and contribute to a sustainable and energy-efficient future. So after my 30 years in the industry, my advice is let's get away from old copycat fluid technology and put the best thermal management fluids in electric vehicles, because I believe there is no excuse for a corroded and unsafe system today. Thank you.
Any questions? Question for Colin? Yes. Okay.
First, your presentation is for knife. Then could you tell me how much your coolant electric conductivity is?
So we have a range of fluids with different conductivities. We have fluids that are under 10 microsiemens, all the way up to 1200 microsiemens, depending on what that fluid is designed for. Obviously, fuel cell fluids and immersion fluids, whether glycol or non-glycol, they're all under 5 microsiemens.
Thank you.
Any more questions? I've got a question. As a technician, how do you evaluate and inspect the condition of the thermal management fluid on an EV? Is it pH, color, concentration, conductivity?
So all of the above, and we have to look at what that system is. Whenever that coolant or thermal management fluid is in an immersion type fluid, conductivity is the main thing that we want to test. So we want to have a stable.
Well, I'd like to say thank you to Colin, an actual
you.
doctor on stage right now.